someone wants to admit everyone from the waiting room, that would be really helpful.
There's a lot of participants. This is not open mic night.
Oh yeah, we usually get about 100 to 125 in Zoom, and then about 20 to 40 on YouTube.
Scrolling through the list of participants. Some people I know quite well, and others I don't know at all. Cool. Some folks from Europe. Wow, I'm honored.
All right, Jerry, I think we're good to go if you want to start sharing the screen, and then I will do introductions.
You see that okay?
Yep, that's perfect. All right. Welcome everyone to today's Magnetosphere online seminar. Today's speaker is Dr. Jerry Goldstein, a senior program manager at the Southwest Research Institute and an adjunct professor of physics at the University of Texas, San Antonio. Dr. Goldstein got his PhD at Dartmouth College, where he studied the theory of cavity resonances of the Earth's magnetosphere under the guidance of Mary Hudson. At the Southwest Research Institute, Dr. Goldstein specializes in the dynamics of the inner magnetosphere and using global imaging observations from missions such as IMAGE and TWINS. He complements this data analysis with both theory and simulations. Dr. Goldstein is currently the Science Operations Center lead for the TWINS mission and is a fellow of the AGU and a 2006 recipient of the James B. Melcoin Medal for significant contributions to geophysical sciences by a young scientist of outstanding ability. So today we are grateful to have Dr. Goldstein discussing the rediscovery of the plasmasphere, history and future of plasmaspheric research. Thank you, Jerry, and if you would like to start.
I will indeed. Thank you for that introduction. I should mention the great time that I had as a postdoc at Rice. I noticed there are some folks at Rice. Hi everybody. So here's what I'm going to talk about today. A large number of slides, over a dozen, where I talk about the discovery of the plasmasphere up until now, the history. And then I'll briefly run through some recent results of my own on this topic, and then discuss open questions and the possibility of future missions to study the plasmasphere. So here's the plasmasphere is the green part, and it's occupying the innermost part of the magnetosphere and is enveloped and penetrated and permeated by other plasmas such as the ring current, the radiation belts, contained entirely within the magnetosheath there you see on the left. This is according to the standard Rice doctrine that the sun is on the left. And folks on the STORM mission team will recognize this graphic as one which I've suggested as a possible mission logo graphic. So that's the neighborhood that we're talking about, is the innermost part of the magnetosphere. Now you'll notice in that previous picture, there's just kind of this smooth laminar plasmasphere picture. That's usually how the plasmasphere is depicted. If any irregularity or asymmetry is presented, it's usually in the form of plumes, which in this side view diagram is represented by this kind of broad day-side region of green that's penetrated by a weaker day-side ring current. Here's a more recent graphic that I put together to kind of capture how much more dynamic this region is than is usually depicted in even just artwork, but also in observations. So you've got the main plasmasphere torus, but here depicted are multiple striations intended to represent visually the large amount of density structure inside the main plasmasphere torus. In fact, there are no observations of the dense region inside the main plasmasphere torus that do not contain evidence of aliasing of structures that were not resolved by the temporal cadence of the instrument. I have never seen any measurements that did not indicate that there was more structure than being measured by the instrument. So that's striation is supposed to capture that. And you don't just have a necessarily isotropic region. You have in the outer region of the plasmasphere on the day side, you may have a trapped population there, but you also have these green things coming out of the ionosphere. You've got day side outflow. You've got the possibility of oxygen as well. The green stuff is kind of representing the H plus and the He plus, the light ions, which is the majority nominally. But during some conditions, you get enhancement of O plus, known as the dense O plus torus, which is shown here in this diagram on the night side, although it can occur at all local times. And how is that dense O plus torus populated is still an open question. So I have two mechanisms depicted here graphically, where you have the cusp ion fountain of oxygen coming out in the cusp region and being dragged over the polar cap, and direct outflow from the night side auroral and subauroral region, mostly subauroral in this diagram. There's also a plume shown in this diagram, but not the typical drawing of a plume. It's supposed to indicate the extraordinary degree of turbulence and fine-scale structure that you see inside plumes. Also, always evidence of aliasing of structure that we haven't resolved with all measurements. So it's a very dynamic region. It's always often described as the cold, dense torus of ions, with whose outer boundary is the plasma pause, but there's a lot going on in this region. Why do we care about this region? A question once asked of me by Thomas Zurbuchen after I gave a Plasmasphere seminar at University of Michigan. He said, "Great talk, but why don't you talk about something people care about?" So here's why we should care about the Plasmasphere. The main answer, a main basic physics answer, is because of mass and inertia. The Plasmasphere carries the majority of the mass and inertia of plasma in the magnetosphere. So here's a calculation from a recent paper of ours, which is cited below, where we made some simple assumptions and axisymmetry, and you get that within the plasmasphere are tens to hundreds of metric tons of plasma. The total is the black line versus L shell, so that's what's enclosed at each L shell. The H plus is red, the He plus is green, and 1% oxygen curve is shown there too. And you can see stuff increases, the mass increases as you go outward. Of course, the larger plasmasphere you have, the larger it is, but you kind of have most of your growth in the L of 3 to L of 4 region. Most of the mass is carried by the protons for 1% oxygen. But if you increase the oxygen enrichment to just 5%, then the contribution from O plus becomes equal or comparable to that of protons. So ion composition, very important here. And this mass and inertia, multiple theoretical and observational studies show how this exerts a controlling influence on essentially on fundamental wave modes. Here's a brief summary of why this is important, mostly from a space weather perspective. First, plasmaspheric mass controls waves and other space plasmas. So the changing size and shape of the plasmasphere region, which is shown schematically by, these are actually data, but it's just kind of, I'm not going to talk about the data. It's just showing different shaped plasmasphere boundaries seen from above the North Pole. So first, the high density region in the plasmasphere is a region of reduced spacecraft charging. That's important for space weather. Second, the plasmaspheric mass within that boundary is a major control of Alfvén waves, which that's a fundamental means of propagating energy through geospace. Here's a plot from Takahashi and Anderson 92 showing how the Alfvén profile is fundamentally altered as you go from outside the plasmasphere to within it. You basically lower the Alfvén speed, and that's really important. The plasmasphere density region also is the region where you have or don't have waves that cause loss of ring current and radiation belts. Here's a plot showing some results from Baker et al. 2004's important, now classic paper on dramatically, severely eroded plasmasphere being associated with a reduction in the loss term, the His loss term that controls the inner axis of the outer electron radiation belt. And here's another paper from Spasiewicz et al., well, a couple of papers showing a correlation between subaraural proton arcs, that is evidence of subaraural ring current ion precipitation that is correlated with the location or boundary of plasmaspheric plumes. So in this regard, the region of losses of energetic particles, or the region where you have reduced acceleration or energization of energetic particles, is fundamentally controlled by this plasma. So we care. Way back during the discovery phase of the plasmasphere, much less was known about it. And so these early studies, which are all of them are classic papers by now, show that the plasma pause is a steep boundary and an otherwise kind of exponentially dropping density profile. That steep boundary was viewed with suspicion by the Soviet Academy of Sciences, so much so that they thought it was the mistake in the data analysis and delayed publication of Konstantin Gringauz's discovery of this boundary, saying that it was unphysical and couldn't be right. So this result was scooped by Don Carpenter's publication of the plasma pause results. And then the location of the plasma pause was early on noted to be farther out on the dusk side and farther in on the dawn side, a global shape of the plasmasphere that's come to be known as the dusk side bulge. And the plasma pause moves inward with increasing magnetic activity. And it's this latter result which is really just a remarkable correlation, which is now again from a classic paper by Rick Chappell in 1970, but of course was reproduced in the Kibelson Russell textbook as well. But this is, of course, a super important result. And unfortunately, what happened, though, was that this result seemed to somehow encourage a pseudostatic view of how the plasmasphere evolves. This correlation of large plasma pause for low activity and small plasma pause for higher activity was explained by a simple paradigm model in which you have a balancing of convection, which is driven by solar wind conditions, and co-rotation, which of course is not externally driven, but is associated with the rotation of the Earth and the magnetic field line with it. And so you get this kind of teardrop shape, and it was envisioned that when geomagnetic activity increased, that is, convection increased, they usually described mathematically in terms of the dawn to dusk pointing convection electric field. When that increased, this teardrop shape would decrease, and then you would have plasma that was eroded. But it was usually depicted in terms, at least as I remember it, usually depicted or described in kind of a pseudostatic way, that you just kind of imagine that the plasma pause, the last closed loop of potential would move inward and all that plasma would just go away. But in fact, that isn't what happens. It takes time. It takes many hours for that plasma to go away. And here's a simple test particle simulation of my own, where you can see it takes many hours for the new, when you move that last closed loop of potential inward, it takes many hours for the plasma to come into equilibrium at all magnetic local times. It happens first on the night side and then slowly over the course of a day or so, at least, to come into equilibrium and get a new teardrop shape. This dynamic process was depicted in the very first simulation models of the plasmasphere by Grabowski in 1970 and several follow-up papers by folks at Rice. But nonetheless, it was, and so this is the early test particle simulations by Grabowski, some follow-up papers by Chen et al. In 75 and others, showing that in the process of erosion, you have many, many hours of a non-equilibrium state where you have plumes and other structures. And for decades, in fact, other models, mostly spearheaded by the Rice folks, the Rice convection model and magnetospheric specification model, that's the latter being what is what I worked with as a postdoc, and showing that plumes are a consistent feature of these models. And yet, despite that, for many years, the quasi-static view of sort of moving instantaneously from a large plasmasphere to a small plasmasphere seemed to, if not prevail, then be quite common. There was also the concept of shielding. This early concept, which I always viewed as a manifestation of Lenz's law, that when you try to perturb this electrodynamic system by convecting plasma earthward, the plasmas and fields respond in a way to try to reduce that perturbation. And so here's this plot from an early paper showing the shielding effect, where you distort the inner edge of the plasma sheet, you generate field-aligned currents through the ionosphere, and you generate an opposing electric field that counters that of convection. But it takes time to set up these region 2 currents. All of the theoretical estimates said that. And because it takes time, you often and probably usually have a dynamic imbalance between the strength of the shielding electric field, which is countering that of convection, and that of convection itself. They tend to be in imbalance. So perfect shielding would have a perfect balance, and you'd have this nice green region here. This is just a schematic, but what tends to happen is the solar wind and IMF conditions change very rapidly, and you get undershielding, that is partial penetration past the shielding barrier. This is what is often known as the penetration electric field. It's really just the convection electric field that's leaking through any attempt at shielding. And then when the solar wind and IMF conditions, when convection decreases because of changing solar wind and IMF conditions, then shielding can temporarily be too strong. It's pushing back against a field that is no longer there, and so it's actually pushing in the opposite direction. And so you can get overshielding. And that is entirely within the early predictions of this hypothesis of shielding. And nonetheless, the quiescent picture persisted, that it was widely discussed that the inner magnetosphere was, quote, well shielded. So much so that this straw man argument was argued strongly against in a 1998 paper by Rowland and Wygant, or Wygant and Rowland, I can't remember. There were two papers, and I can't remember which one, but the paper was arguing that shielding couldn't be, was kind of arguing that shielding couldn't be valid because they were seeing large electric fields at lower L values, and presumably that you shouldn't see them. But in fact, those electric fields, what are now known as penetration electric fields, are entirely within the paradigm of shielding if you understand it as a dynamic process. So this quiescent and static picture of the plasmasphere failed for a long, long time. When I graduated, got my PhD, and started the image mission, that was kind of the status of things. I remember as a grad student studying cavity modes in the plasmasphere, and one of my fellow grad students said, why are you studying the plasmasphere? It's so boring and quiet. And I thought it was super cool, just to, even if it was quiescent, to study the cavity mode resonance, which to me was kind of like music. As a musician, I appreciated that. But it turns out that with the image mission, we were able to see this is a far from quiet and far from boring region. In fact, it's super exciting, and image mission results really show that. So when IMAGE was launched, it was the first time we had the ability to do routine global imaging of the plasmasphere. And this is an image from 2002 event, but we have many more from very early on in the mission that I'm going to just briefly review. And it was, for me, a real eye-opener as a postdoc at Rice to see for the first time this region that I had been looking at through various passes of spacecraft measuring in situ density and other parameters, but mostly density, to see this whole region at once. So in these images, the sun is usually to the right. Sorry to the Rice folks. And then there's often a shadow on the night side, because what you're seeing is resonantly scattered sunlight, and so this resonantly scattered sunlight doesn't reach the night side as efficiently. And so you have a little bit of a shadow. But there's a plume on the dusk side. There's the main plasmasphere torus. You're looking down on the North Pole here. So what were some of the things we were seeing? One of the first things that I was studying as a postdoc was the plasmaspheric shoulder. And this was a feature that was very, very unexpected, except if you read a 72 paper by Carpenter and Stone, you'll see that it was predicted actually based on ground-based Whistler observations, but could not easily have been observed using those observations. But for anybody else who wasn't reading the early literature, this was a real unexpected feature and unexplained. And using the Rice magnetospheric specification model, which I very poorly understood at the time, and most of the real insight into the physics going on in this, or being represented by this model, was that of Dick Wolf. Still, what was happening was overshielding, is that the IMF turned northward, and you all of a sudden had a situation where the shielding was pushing back too hard, and you have this dusk to dawn pointing shielding electric field. It's kind of like a two-cell convection pattern pointing in the opposite direction. And when you add that to co-rotation, it produces this shoulder shape in the flows that, if you just take those flows and superimpose them on the shape of the shoulder actually observed, it really produces it quite well. So this was graphic, literally graphic representation of the fact that shielding is a dynamic process and not a static one. And then there's plasmaspheric erosion, this dynamic process that takes many hours to come into equilibrium with the new solar wind and convection state. And of course, the solar wind and IMF are always changing and fluctuating at least, but sometimes changing dramatically. And so coming into equilibrium is kind of a funny thing. It's probably never quite in equilibrium. These were the first global observations using image of the erosion process. And you've got the night side, you can see the shadow of the Earth. The day side, there's this neutral helium day glow mostly that's much, much more intense than the target emission at 30.4 nanometers, and it's leaking through the filters. So that's, you can always tell where the day side is by looking at that. And you can see the night side plasma pause in this movie starts out quite far and then erodes inward significantly, and then a plume forms on the day side, which is partially obscured by a blackout in one of the cameras caused by sunlight contamination. Now, this is a very interesting event. First of all, it was super exciting to see for the first time an actual erosion happening on a global scale. And if you compare this with the convection-based models, they do a pretty good job. Even the simple, poorly constrained ones that I tend to use do a pretty decent job of at least describing globally the morphology that you're seeing. But people were so used to seeing the plasmasphere as static that I remember at several meetings during the early image era, people were questioning, well, how do you know this moving boundary is not just a result of the fact that the spacecraft is moving and it's some sort of different perspective effect? People were so used to thinking of the plasmasphere as static that they were not believing the evidence of their own eyes looking at these images. So if you take these images and you map them to standard geomagnetic coordinates, you see quite clearly that the boundary is, of course, moving inward. It's moving in about 2 RE in just a couple of hours. And not only is it moving in 2 RE in a couple of hours, it's moving in 2 bursts. If you watch very closely, I don't know if this repeats or not. Yeah, it moves inward and then pauses and then moves inward again. And it repeats, and you can watch it do that. And if you track that motion as a velocity and then multiply it by a magnetic field, which in this case is assumed to be a dipole, you get 2 bursts of basically convection electric field. And those correlate with southward turnings, 2 bursts of southward IMF. So in this case, you have the southward turning of the IMF that's directly driving the erosion. When the IMF turns to 0 instead of southward, the erosion pauses. And then the IMF turns southward again and the erosion recommences. So this is direct driving, but there's a time delay. It takes time for the southward IMF at the nose of the magnetopause to propagate over the cusp, over the polar cap and onto the night side. And that delay is about 30 minutes, 20 to 30 minutes statistically. We've seen this delay from magnetopause to night side, so I'm calling it the MNP delay here. We've seen that on every single erosion event ever witnessed by imaging UV, that it's directly driven by the IMF changes, and there's a 20 to 30 minute delay. And of course, severe plasmasphere erosion, such as I already mentioned Dan Baker's 2004 paper, where the plasma pause started already at sort of a nominal value of about L4 and was eroded down below 2 RE. basically almost removing the plasmasphere entirely, pretty much refuted the idea of a well-shielded plasmasphere, and of course pointed the way towards more widespread appreciation of the cold plasma's effect on relativistic electron global distributions. So the plasmasphere, we now know, goes through a cycle of erosion and recovery. Every time there's a disturbance, even a mild or moderate disturbance, there's some kind of response to the disturbance. And there's a repeatable pattern where you start with a large plasmasphere and it erodes to a smaller plasmasphere with a plume. The plume is the signature of the fact that the erosion process is dynamic and it takes time for all that tens of metric tons of mass to clear out of the inner magnetosphere. And then during recovery phase, the plume that was there rotates and wraps around the main plasmasphere, and then you gradually refill to a larger plasmasphere. And if you extract plasma pause boundaries from these images, you get a mathematically represented or quantified representation of this cycle of erosion and recovery, and you can plot it versus various input parameters like delayed interplanetary magnetic field, delayed by, I think in this case, 20 or 30 minutes, I don't remember what. But the point is you can correlate these changes clearly to changes in the IMF, which is a gate to the coupling between the solar wind and the magnetosphere. So decades of modeling studies have predicted these plume phases, starting with Grabowski's 1970 paper, going through the studies using the Rice developed MSM model by Lambor and Weiss, the results in 1981 or 1982 published by Bob Spiro and others. Much of the work on this modeling was being done by these folks at the Rice University. Decades of modeling studies have predicted these plume phases, but IMAGE was able to see them for the first time. And it was really satisfying to see such a nice concordance between models and observations. That's not to say that everything's answered. It's just that global morphology and the repeatable pattern was predicted by these models. But there were crucial differences between the models and the observations. Very important to remember that, because not only does it tell you that the convection models that we're using are insufficient, but it also tells you that there are processes, maybe even some microscale plasma processes. Some have indicated a possibility of interchange instability or other plasma instabilities or turbulence being important. So I made this plot of interest in the plasmasphere, which has waxed and waned with time. And to do this plot, I just basically did search terms for plasma pause or plasmasphere by year on ADS. And so these are the papers whose abstracts or titles contain the term plasma pause or plasmasphere, starting with its discovery, when people were usually discussing Carpenter knee, which is the old-fashioned name for the plasma pause. And you can see with these early missions, OGO 5 and IC1, interest was rising rapidly, and then there was a gradual decay in interest during the polar mission through D1 and crest down to the polar mission, when the interest in the plasmasphere was at an all-time historical low, except before it was discovered. And that was right when I was getting my PhD. So all these comments from my fellow PhD students at Dartmouth saying they weren't interested in what I was doing was echoed by the entire community. People didn't care about this. And then IMAGE happened, and interest in the plasmasphere grew larger than ever before, and it's been increasing ever since. With Van Allen probes, it's been just historically the largest interest in the plasmasphere ever since the discovery, and that is because of its profound influence on the more energetic particles. It's because of that influence that the HOPE instrument was included on Van Allen probes, and its ability to measure ions down to 1 eV or so. Of course, there's a spacecraft potential to overcome, which there's no compensation for on Van Allen probes. But the interest in the cold plasma was there. At least trying to see the tail of the distribution above the spacecraft potential was something that was argued on the basis of the important physics. My own research on the plasmasphere, I started in cavity modes, then I got interested in density and overshielding. I got interested in plume and plasma pulse dynamics all on their own using IMAGE data. and their influence on the ring current and radiation belts. And then after IMAGE died, I did a lot of plasma pulse modeling for a long time. I looked into some new EUV imaging techniques and understanding better the imaging techniques that we have already. And then recently I've been revisiting everything and trying to understand what the unanswered questions are. So I have some recent works. I'm going to flash through these quickly because I don't want to go over time today. But I just want to give you an appreciation that my recent work on the Plasmasphere, which is shown graphically here by these different bars, these are start to finish investigations here. I never quite got back to cavity modes, but just about everything else that I've studied during my time in studying the Plasmasphere science throughout my career so far, I've basically hit all these different things at one time or another in recent years. And so I'll just kind of cruise through these quickly. First, even though IMAGE stopped at least communicating with the ground in 2005, December, people have still been looking at these EUV images since then. There have been just not a huge volume, but a fairly steady number of papers that are coming, several per year at least, where people are studying these EUV images, the historical database, even though we don't have any or many new images. So what I did recently in this past year was look at the relative timing between the day side and the night side during the onset. I've already had showed you results that show that IMF changes propagate from the magnetopause to the night side with a finite delay. But here I wanted to know, is there a difference between the motion of the plasma pulse on the day side versus the motion of the plasma pulse on the night side when an erosion first starts? And this was partially something I was working on about a decade ago, and I submitted a GRL, which was rejected on what basis I don't quite remember. I think they insisted I used ground radar data, so maybe the referee was a ground radar person. And then I dug up the manuscript just this past year and said, let's try again. And so I submitted it and got it published in JGR. We added a second event, actually, to this first one. And basically what we find is that the day side and the night side move together within the time resolution of image UV images. That is, they're simultaneous within a 10-minute uncertainty, plus or minus 5 minutes. So that's not to say there isn't a time difference, a delay between the day side and night side response, but that it's shorter than 10 minutes. And that has important implications for the erosion mechanism, especially if you wanted to, this particular event, if you wanted to attribute it to interchange instability, this near simultaneity would require, you can read the paper and see where I get this, but would require a day-side ionospheric conductivity that might be a little bit unrealistically low. That's not to rule it out for every, this mechanism out for every event, but for this event it seemed unlikely. So you can get important information about how energy propagates through the system this way. Does it get imposed on the whole inner magnetosphere at once it propagates to the night side, or would it be on the day side first, as you might expect, since information is propagating from the magnetopause to the night side? And we need finer time resolution imaging to resolve that question. So we hope to get that someday. I have been running plasma pulse test particle simulations. I have been for years, for over a decade, telling people that my test particle simulations are terrible and they're only to be believed with a huge grain of salt. Nonetheless, people are using them, especially in support of Van Allen probes emissions. So I thought to quantify the uncertainty of the models predicted plasma pauses versus the observed plasma pauses. And the agreement is within plus or minus 0.4 RE, which is not fantastic, but it's not super terrible either. And also we found there was, in this one study, we found a residual plume was predicted by the model, which is shown in this right diagram here. The green region here in the equatorial plane there is the model, and then the vertical axis shows the observed density. And what we saw was a residual plume that was like 32 hours old, and there was evidence in the in situ electron density that there was actually a little filamentary plume there. So this says plumes can last a really long time. They can rotate and wrap and last for tens of hours. This led me to wonder, actually I had been wondering for many years about the importance of pre-existing structure in the plasmasphere. And here's an example. If you start a simulation with a round plasmasphere, an O'Brien and Moldman 2005 model plasmasphere, and you compare to the observations of Los Alamos orbiting spacecraft, so that's these circles here get darker color when the observations are showing plume plasma. You can see the observation says that this L1 was seeing plume plasma, or at least cold dense plasma, and the model says that it should be in the trough. And that's, as I show in a second, entirely due to the fact that the initial conditions were unrealistic. It's only when you're really driving the system harder that you're starting to get a plume in the model at the same location where there's clearly one in the data. Now, in this second simulation, everything's the same except the initial condition is taken from an image UV image. And you can see a lot of structure here as well. And now watch as this pre-existing structure gets elongated and deformed by the even mild convection. Now look at the structure of these filaments and then look at the structure of the density here. It's very evocative of, they're very evocative of each other. And I think I interpret this modeling study, which is unpublished, by the way, to be evidence that to some degree, not entirely because there's of course dynamics going on, but to some degree pre-existing structure can get elongated and survive. And remember, this is a simple simulation where I only had one contour of density, but in fact the real plasmasphere has a vast reservoir of fine-scale structure to draw upon and always be feeding it into plumes. This was a recent paper where we showed that you could make a slight modification to the existing heritage image UV camera by changing a coating on a mirror and changing the material of a filter, and we would be able to image the O+ dense oxygen torus. So here's a simulated image of what you would see after the torus forms based on some historical data from the Roberts et al. 1987 paper. And so we're very excited about the possibility of imaging the dense oxygen torus at some time in the future, and that's what this paper was all about. I won't dwell on this, just to say that I think that epoch time, that is the time, the phase of the storm, is the way to drive plasmasphere simulations, and I put together an epoch-based model. It's also based on analytical equipotentials of the Coulomb-Stern convection field, and it gets, actually, it's agreement between this epoch-based model and the full dynamic simulation is about the same. The agreement between this and the Van Allen probe's plasma pulse data is about 0.45, so close to the same performance as the full model, and a lot easier to use. I also looked at the temperature dependence of cold ion composition and found a couple of things. The light ions behave as you sort of classically expect, with a dense main torus and an outer plasmasphere that's not as dense, or plasma trough, and they tend to be colder. Oxygen ions tend to be warmer, and the spatial distribution is very, very different. You have a steeply falling profile and then a dense torus. So the dense O+ torus is located right at the region where the light ions tend to be tapering off. So these are different ions getting, the light ions versus O+, they're getting into the magnetosphere very, very different ways. The H+ and the He+ getting through sort of classical refilling, and then the O+ requires an extra heating source, and thus the O+ temperatures tend to be about an order of magnitude higher. So they're very, very different populations, even though they're spatially coexisting. And we found that the ion concentration of H+ and He+ don't vary very much with temperature, but O+ the concentration increases steeply with temperature. And so that's consistent with what I was just saying. And you can use these results to correct the HOPE ion density measurements, the partial ion densities. If you have the total electron density measured by the upper hybrid resonance, you can scale up these ions. You can generalize these results to do a simple and not entirely unbelievable correction to the observed ion partial densities. So what's left to learn about the plasmasphere? There are still fundamental gaps in our understanding of refilling and erosion. We we really don't understand totally how core plasma, that is our way of talking about cold plasma, we call it core plasma, because we want you to know how important it is. How does this core plasma fill the inner magnetosphere? And how is the plasmasphere eroded and redistributed during geomagnetic disturbances? Those are major science objectives. And then questions. Basically, these amount to, the first question is, how is the plasmasphere replenished? That is, in detail, how does this happen? We have never been able to sample moving flux tubes. Spacecraft trajectories don't follow moving ion drift trajectories, as you can see by this comparison between just a simple Wallenstern convection field and geo orbit or Van Allen probe's orbit. None of them are really following. The ions do not follow strict co-rotation, so if you try to use geo observations, you're really missing a lot. And of course, most spacecraft are just cutting through the distribution. So we really don't know how individual flux tubes refill in detail. How does their density increase? How does that density increase vary versus geomagnetic activity and versus composition? Also very important. First steps at this were understanding this were taken using global imaging, but we need to use more sophisticated inversion techniques that have recently become available with the publication of two 2014 papers by Nakano et al., where we can actually follow individual flux tubes now. And then this is super exciting and interesting to me. How are ions trapped during refilling? You've got these beams of ions coming out of the ionosphere, presumably conjugate, although not necessarily equal, coming from both hemispheres. And if they stay as beam distributions, they're just going to keep going and go back into the conjugate ionosphere, and they're not going to maintain a stable population of trapped ions that we know is there. So how do you go from beams to trapped distributions? And on the right-hand side here, you see some early DE1 RIMS observations of beams coming out of the ionosphere, H plus and HE plus, so your classic refilling. And how do these beams become isotropized or heated, as they're often described? It's three mechanisms possible: shocks, wave scattering, or Coulomb collisions, and we don't know the answer. Models suggest various things, but the models need to be constrained by observations. So we really need to measure the cold ion distributions, the pitch angle distribution functions, and compare them with the most sophisticated models we now have to answer this question. And then I talked about this already. What causes the dense oxygen torus? What is the pathway for these O+ ions to populate the dense torus? That is the colder part of the oxygen population that is sort of hugging the plasma pause boundary. And how do they get there? Are they coming out from the day side, out of the cusp, and then being convected onto the night side, in which case they would have non-gyrotropic pitch angle distributions? Or are they coming directly out of the ionosphere on the night side, in which case they would have field-aligned distributions? And there's another big question that we need to answer. And then convection, how does that redistribute core plasma? You have tens of tons of plasma being moved around during convection, and we have numerous features of in the EV images as well as in situ observations that we can't explain with our existing models, and we don't understand what's causing them, and we don't even have them well characterized. We don't even have a really accurate and quantitative zoology of what's coming out during convection, and so we need to understand that better in detail, and much of that involves our understanding of the inner magnetosphere convection field. So you have this zoo of recovery phase structure, especially, not just during erosion, but during recovery. We have, remember I showed you that teardrop shape? I've never seen a teardrop. And in fact, these are Rorschach tests. These are not teardrops. These are, you can see whatever you want. You know, here's my dad. Here's, looks like a little cartoon character. These are not smooth laminar shapes. And we don't understand what's causing any of this structure right now. Finally, it's an enduring question: what role does interchange play in erosion? And there are concrete predictions about the global shape of the plasma pause boundary. If interchange is playing a major role versus if convection is really driving most of the erosion process. And so we really need to put end to this question and understand what role does interchange play, because this question hasn't gone away. So this was a mid-X mission. These questions that I'm talking about were proposed in a mid-X mission. We did very well. We were rated selectable and then a programmatic decision was made where we weren't selected. We were disappointed about that. I'm not going to say that we weren't, but we're very encouraged that we will be able to get a mission dedicated to studying the plasmasphere up as soon as possible that would combine imaging with in situ observations. So imaging to get the big picture that I've been showing you, but the in situ observations, we really want to get those ion pitch angle distributions all the way down to 0 EV. And the way that we want to do that is to control the spacecraft potential. So here's a simulation done by Gianluca Delzano in a paper that we're trying to finish revising this year, where you can, this is a Van Allen probes modeled spacecraft where you negatively charge one face of the spacecraft to make a pathway for the coldest, the 0 EV ions to get into the HOPE instrument. And you step through different negative voltages to get different parts of the distribution function. So you do 0 EV to get the full, to get a good measure of the warmer ion temperatures. You do step through all the way up to minus 30 EV to get a full density. And these 4 measurements that you make in rapid succession allow you to fully characterize the pitch angle distribution of the coldest ions. So that's a really big part of what we want to do in this mission. And we also want to do global imaging of both the helium ions, those are the green images, those are the ones that flew on image, the 30.4 nanometer, but also the oxygen images that I told you about. We want to fly one of those O+ imagers at 83.4 nanometer wavelength and measure the global distribution of oxygen. So I'll finish by saying that it would be really also nice to study the plasma spheres of other planets with global imaging. And this was a white paper that I submitted for consideration as a possible auxiliary instrument on the Io volcano observer. They didn't have room for it, but Alfred McEwen considered it very graciously. So the idea is to just keep the same. We have a flight spare image UV camera that we could just bolt onto a spacecraft. We have the electronics as well. All we would have to do is change the mirror inside, change the coating, and this super bright signal from the Io plasma torus at 275 Rayleighs at the wavelength we want to look at is, so the signal to noise ratio can be about 100. So this is much better than the situation as very low signal to noise ratio that you get, much lower signal to noise ratio you get for image UV and especially for O+ imaging. And we want to know if the simulations are right. They predict a great degree of finger-like structures at the outer edge of the Io plasma torus, and we'd like to image that and study it and compare it with Bryce convection model for Jupiter and other global models. And something similar might be done for the plasma torus at Saturn, although I haven't looked into it quantitatively as much. So the past 2 decades have witnessed this resurgence of interest in and investigation of the plasmasphere, as I've been trying to describe to you, and there's much more that needs to be done. I think a programmatic decision that said that the plasmasphere mission was less desirable, that just tells me that I need to get the message out better. We need to have the community appreciate better how fundamentally important this science is and how we really need to do it. So I think I'm at 10 minutes to the hour, and I'll stop presenting now and open the floor for questions.
Great, thanks, Jerry. That was a wonderful talk. I have a handful of questions, about 10 or 12, that I can read to you. I will note some of them do directly address your open questions, so might not be answerable at this moment. So the first one comes from Sergei Apatenkov. What happens to the mass and energy during the erosions and expansions of the plasmasphere? Where and how is the mass and energy lost or obtained?
Well, that's something that's been not well quantified. The most estimates for what the mass are in the order of the simple calculation that I did. But I think what's happening is that you have a really much vaster reservoir of mass in the ionosphere that's resupplying the plasmasphere after erosion. So you've got all of this plasma that's being stripped off the night side and then funneled toward the day side in the form of plumes. And then this increased mass density lowers the alphane speed within the plume region. And then when that lowered alphane speed reaches the day-side magnetopause, there are multiple papers suggesting that this can have an impact of some kind, maybe 10, maybe 20 or 30% even on the reconnection rate. By slowing the alphane speed, you might be slowing the reconnection rate. And then this mass, it's believed, is vented into the magnetosheath and into the solar wind. Maybe some of it along the low altitude part of the field line makes it back onto the night side, and maybe some of it makes it into the plasma sheet. Some simulations by the folks at Goddard have suggested that as well. So where does this mass go? I think a large part of it gets stripped away and brought to the day side and dumped into the solar wind, and then it's replenished from the ionosphere slowly and unevenly over the next several days after a disturbance. Does that answer your question, Sergio?
I think so.
Okay.
Sorry, we usually leave people on mute and we just read them out.
Cool. So that I must have been totally successful. He said nothing. It has nothing to do with him being muted, I'm sure.
So our second question comes from Trunali. How do substorms, and in particular isolated substorms, affect the plasmasphere?
Good question. I've only partially studied that, and what I've seen is that there are two things that can happen. One is, most commonly what I've seen is that substorms that tend to happen in the recovery phase, the plasmopause is already kind of eroded on the night side, and what the substorm causes is a wedge of ripples to start propagating across the magnetopause. So it will kind of perturb and wiggle the plasmopause boundary, and you can track the motion of that ripple as it propagates both eastward and westward. Incidentally, the eastward and westward propagation of those ripples are the same spatio-temporal locations as the eastward and westward propagating motion in the auroral boundary. I showed that in a 2005 paper combining imaging from auroral imaging and plasmopause imaging. So what happens during substorms is you get a burst of convection. And if the plasmopause is already eroded, if it's an isolated substorm, then you will see ripples propagate across the boundary, but then the boundary will move back to where it was before the substorm. But if this is not an isolated substorm and the substorm is part of the buildup of the storm, then it's part of the erosion, and then it's sort of factored in. And in fact, that two-phase erosion that I showed, one could argue that those were two substorms. In one paper of that event, we showed that these two successive erosion steps of the plasmasphere on that July 10, 2000 erosion were coincident with peaks in the AE index, suggesting that, you know, it's a substorm activity.
Cool. Our next question comes from Marissa Headland. She asks, are there any constraints for erosion mechanisms on the night side? Maybe things such as the Peterson conductivity limit listed for the day side?
Interesting. In my studies, I focused on the ionospheric conductivity as important, not for the externally driven, I won't say it's not important, but my focus has not been on its importance for the externally driven part of the convection field. But rather, I have focused most of my attention on the importance of the ionospheric conductivity for the feedback. So you've got these region 2 currents at the east and west boundaries of the partial ring current going into and out of the ionosphere and creating their own electric field that modifies the convection field. And that's, of course, part of shielding as well. And I have found that the ionospheric conductivity is important for that feedback mechanism. I haven't given sufficient thought to how the ionospheric conductivity is important for the overall driving, although it's certainly important for the timing of the day to night delay of the erosion onset as you're dragging field lines through a denser or not dense ionosphere. That, of course, will be different. And the original Coroniti and Kennel estimate of 20 minutes for the day to night delay, which is pretty close to what we observe, talked about the importance of ionospheric conductivity there. So kind of a sketchy answer here. I think it's important, although the degree to which it's important is not fully known by me right now that I think about it, because I have focused on other aspects of it.
Great, thanks. So our next question is from Katrina Nakuri. Does the fine hairy structure with the plume on the dust sector correlate with the energetic electron microinjections?
I do not know because I never published that simulation and I never looked at particle data. But here's what I do know. Simulations for many years of RAM-SCB by Vanya Jordanova and others have shown that, and also some recent work, well, for me, getting up in years, recent work is maybe 10 years ago. Lunjin Chen did some work on this too, showing that ripples of the density correlate. The gradient, where the gradient is steepest, is where you see the growth of waves that can pitch angle scatter both electrons and ring current ions. And if you, I have a foggy recollection that if you assume that the density inside the plume is smooth, as was often the case for the RAM-SCB simulations, with which I'm familiar, although there may be some more recent ones that Vanya has done, most of the density gradient occurred at the global boundaries of the plume, and that's where you saw the largest growth of electromagnetic ion cyclotron waves, for example. But if you assume that there are striations of density distributed throughout the plume, then you would expect to see growth of emic waves throughout the plume, throughout the east to west extent of the plume, where the ring current ion distribution is overlapping with the plume, where those drift trajectories are overlapping the plume drift trajectories. And in fact, the observations of subaraural ion arcs tend to bear that out, that those tend to be distributed throughout the plume often, although not always. So I would say there's a strong likelihood that there should be a correlation between striations, fine scale structure inside of plumes, and some kind of microburst, which I'm equating with precipitation in my sloppy way right now. But I don't know if anyone has done that correlation yet.
Okay. So Fabian has a question regarding that same simulation. The plume in the simulation of the fine structure does not appear to co-rotate. Is there a reason for that?
The plume in the simulation of the fine structure does not appear to co-rotate.
Is that simply because the simulation time was short, or?
No, I don't think it was that short. Let me see if I can get through it quickly and efficiently. Let's see if I understand what Fabian is asking. Way back here. Here it is. So I think it is co-rotating. It's just it's far out. I don't know why this. Oh, because you have to go full screen. I don't know why that. I think stuff is co-rotating. If you see, it's moving eastward. It is co-rotating. It's just that these striations in this simulation are outside of LO4, and there's more of, in this crude simulation with just the Wallenstern convection plus the SAPS addition, a SAPS term, which is from our 2005 paper. Stuff is co-rotating. It's just that the co-rotation effect is harder to see. You can see even when the stuff is getting bent over by convection, it's still rotating eastward. So there's still a co-rotation there. I hope that answers. Hi, Fabian, by the way. Thanks for calling in from New York.
All right. So our next question is from Patricia Reef. Is your torus the same as Rick Chappell's cloak?
Hi, Pat. Pat Reif, I think you mean. No, it's not quite the same. I would say that the dense O+ torus is the coldest, innermost part of the oxygen population, and the cloak is sort of tends to be warmer and tends to be outside of where the dense O+ torus. And there's another distinction that I suspect, based on historical observations, but have not yet validated yet with my current study of warm ions using MMS. And that is, I think that the cloak probably has very little, if any, trapped O+. But I think that the dense O+ torus might have some trapped O+. And I have to validate that with a pitch angle distribution study that is currently underway. But I think that's the case. And the historical data seem to bear that out. It's very rare to see anything but bidirectional O plus in the cloak, whereas there are observations closer in on flux tubes that tend to map to the outer plasmasphere and plasma trough region, where there's more of a possibility for a trapped O plus distribution.
Okay, so our next question is from Zenon. How do you interpret the image results? Is it a projection or sum on a plane or a cross-section in the equatorial plane?
How do we interpret them? In my case, crudely. What I do is I take each pixel of the image, and I have a software which I didn't write. I can't even take credit for that. Have a software that was written by Terry Forrester at University of Arizona that basically takes the pixel in each image and maps it to the maximum L shell along its line of sight. And that's the geophysical mapping that we use. And in order for this mapping to be correct, it must be the case that the majority of the contribution for the line of sight integration, which is what you're getting all the photons along a given column density from the imager all the way to infinity. It has to be the case that the majority of the contribution comes from the magnetic equator for that minimum L along the line of sight approximation to be valid. And it's at least 50, sometimes as much as 75 or 80% of the contribution coming from the equator, depending on the pitch angle distribution, of course. So depending on the field line density distribution. So that's the assumption that I use, and it's crudely correct. Although in cases where you're looking at plumes, sometimes that mapping assumption can get a little bit tricky because you have one boundary outside of another boundary. If you look at this image here, you could have a plume whose inner edge is draping over the main torus, which could complicate interpretation of the observations. If you really want to do this right, you have to do a full inversion where you assume, because it's a 2D image, you have to assume what the field line density profile is. If you make that assumption, you can do wonderful inversions like Shinya Nakano has done in his 2014-2015 papers, doing full inversions that do a remarkable, within 10% accuracy with the density. So that's the right way to do it. I've been doing it the simplest and crudest way that I could, and it gets decent results.
So this is my aside, but following on from that, is that somewhere where TRIO would help then, or a mission like TRIO?
Yeah, absolutely. Shinya Nakano is on the TRIO science team and is committed to doing his full inversions, which is much more sophisticated method of analyzing the data. And then we also have experience with doing inversion of images by Joe Perez at Auburn University. He has done them for the more complicated images that you get from twins, which are ENA images and have a lot more things to assume. And when you boil away all those assumptions, you can run his inversion code for the plasmasphere distribution as well.
Cool. So our next question is from David Sybeck. What fraction of interesting events do you think have been published or studied in the image EUV data?
10% at most. Depends how you define interesting. But I think, so let's just say the number of storms during the image solar cycle, which I guess was 23. During solar cycle 23, I don't know how many storms there were, but there were a large number of storms. There were a large number of disturbances. There were numerous erosion events that were not part of major storms, and that's just the active time stuff. So I would say 10 to 15%, well, maybe 30% of the storms and events have been published or studied. And then you have most of the time the recovery phase, the stuff that we really, really don't understand. We have no idea what the inner magnetosphere convection field looks like during quiet times, if the image UV images are any judge, because there's no model that has ever predicted those crazy, crazy shapes of the plasmasphere that I showed you in that zoo of quiet time images. So those events are very understudied. I would say maybe 3% of those events, I would say 1% of those events have actually been studied. And that's where we really don't know what's happening in the inner magnetosphere, or to what extent stuff like coupling to the ionosphere or thermosphere are important. To what extent solar quiet current effects might be important, and plasma instabilities that are eclipsed by very, very strong disturbances might come out like stars during nighttime to really be the controlling mechanism during these recovery phase events. So a very small fraction of the existing IMAGE-UV data set has actually been analyzed.
Interesting, but I guess good news for researchers. So
Yeah.
we have three questions left. We have another one from Sergey. Is it possible to study the plasmasphere by launching tracers like lithium ions?
Of course, it's possible. It would be cool to think about that. Email me, please. I'd be intrigued at what you have in mind. It sounds like what you're thinking about is tracing motion of flux tubes. And boy, wouldn't that be cool if we had some network of injecting some kind of tracers onto flux tubes, and we could image them from far away or something and just follow the flux tubes and not have to do an inversion. We just could see some line. That would be super cool. I think that sounds, I'm not misinterpreting your question, Sergey, then it sounds intriguing. Please email me.
So Sergey, he adds artificial ions.
Yeah, I assumed that. Yeah, there's not much lithium in the real plasma, so I assumed it was artificial.
Okay. So our next question is from Martin Archer. You mentioned that your modeling uses just one density level. Where is the field at in being able to predict the often observed multiple sharp boundaries between the trough and plasmasphere? Or indeed the opposite when the plasmasphere is actually highly extended in radial distance?
It depends. Active time with good initial conditions, it's pretty good. Even with my terrible model, you can, which I should mention, Dick Wolf once said, it's annoying how well the terrible model does. For very little effort, it's even with a terrible model, with decent initial conditions and a reasonable convection field during active times, you can get a pretty good agreement. But during recovery phase and quiet times, we are at a very, very primitive state of understanding. In one of my classes, magnetospheric physics classes that I teach at UTSA, one of the students noticed something, that in the early phases of plasmasphere discovery, features were described in very colorful terms like carpenter's knee and things like that. Shoulders is another example. But when you don't really understand something, you describe it anthropomorphically. You say it's like a part of a body, or it looks like this, or it looks like that. And then you discover the physical process behind it. And you discover carpenter's knee doesn't describe the physics at all. It's just a phenomenological description. And then when I showed this zoo of features like things called crenulations and ripples and fingers and notches and things, one of the students in the class said, boy, it seems like your state of understanding of the quiet time plasmasphere is where the state of the active time plasmasphere was like 60 years ago. And I think that's accurate. We really have no idea what's going on during the recovery phase.
Wow. So two more questions. Derricott, apologies for the pronunciation. Is there a difference between images of the plasmaspheric structures as observed from either the north or the south?
We haven't had a lot of chance to look at conjugacy because most of the observations were obtained from a polar vantage point. There are some side view images of the plasmasphere that have been obtained, wonderful images obtained from the moon by the Chang'e 3 EUV imager. But the non-conjugacy has been, in terms of analysis, has been eclipsed by attempts to use north-south asymmetry to infer local time distribution, which baffles me, but it's some sort of magic they're able to do it. At least credibly. What I expect to see if there's a non-conjugacy, is that dayside summer hemisphere would have more outflow than dayside winter hemisphere. But I don't know of any images that have indicated anything like that. So it's very understudied.
Okay. And so our final question comes from Drew Turner. I think it's a
Hi,
follow-up
Drew.
to David. Has anyone applied image pattern recognition approaches, such as machine learning, to categorize the image data?
No, not yet. Irina Zhelevskaya, who's at Potsdam working with Yuri Spritz right now, and I'm on her thesis committee. She's going to defend extraordinarily successfully, I predict, in just a couple of weeks. She has applied machine learning to the analysis of both imaging UV data and a reservoir, mostly of Van Allen probes in situ data, and has done an extraordinary, groundbreaking job of really advancing the state of the art. But in terms of categorizing features, like what I've been saying, and sort of classifying them like a zoo, no, she hasn't gotten that far yet. She's only, updated like 2 or 3 paradigms, not all of them. But I would predict that her approach could be broadened to do that type of categorization.
Cool. So that brings us to the end of the questions that we have today. Thank you for a wonderful talk, Jerry. That was really informative. And thank you for answering all of the questions. That was generally a few more than we usually get. Next week, we have Angeline Burrell, and she will be discussing Python in space physics for all of those who might be interested in moving from MATLAB and IDL to something more open source. And the week after that, we will have a break due to the holiday weekend. Thanks again for a wonderful talk, Jerry.
You're welcome. Thank you, everybody, for attending.
Have a wonderful weekend, everyone, or a wonderful week, sorry.